Welcome, everybody. The Terzaghi Lecture is one of our great features that we have each year, and it's a special treat for me to be able to give the introduction, and thank you very much, Phil, for allowing me to do this, and I'll share that with you next year when I'm president, and you can have your turn. But this is a special time because this is part of our academic family that I come from. Our speaker tonight, David Daniel, is the fourth president of the University of Texas at Dallas and the second sitting university president to give the Terzaghi Lecture. Dave started off his career as a practicing engineer at Wilbur-Clyde. He came back from Wilbur-Clyde to the University of Texas to complete his PhD and joined the faculty shortly thereafter. Spent 16 years climbing through the academic ranks. In 1996, moved into a leadership role at the University of Illinois at Urbana-Champaign as the head of civil engineering, sitting at Nathan Newmark's desk in the department. And after his term as head of civil engineering, he moved on to be dean of engineering at University of Illinois, and then in 2005 moved into his current role as the president of the University of Texas at Dallas. Dave's had a storied career. He's collected many of our awards throughout the years, the Norman Medal, the Crowes Medal twice, the Middlebrooks Award, the President's Award from ASCE, the GI Heroes Award, and the Opal Award for Education. He's also been a recipient of other awards, the UT Academy of Distinguished Alumni, and in 2000 elected to the Academy of Engineering, the National Academy of Engineering. Dave's also been in a number of notable service and leadership roles, serving as the chair of the ASCE External Review Committee on the Katrina investigation, and also more recently on the National Academy's panel on the Deepwater Horizon explosion. He's also served as the president of the Academy of Medicine, Engineering, and Science of Texas. Dave's had a wonderful career, and this is a great opportunity to honor you. I like showing these trees. I showed one like this yesterday. I took my own picture out, so I'm not relevant tonight, but the same lineage. And if you're a Texas X, look for a subtle difference in this diagram tonight. But you can see that Dave's a direct descendant of Terzaghi, coming through Ralph Peck, Roy Olson, and then Dave. Dave has been a leader and a pioneer in our profession. In the 1980s, the topic of geoenvironmental engineering was really in its infancy, and many today would consider Dave and perhaps a couple of others as a father of geoenvironmental engineering in our geotechnical profession. In the 1980s, this was a relatively new area, an area in which most geotechnical engineers had very little training. And Dave was out at the forefront, lecturing, educating both engineers in graduate school like myself, but also a lot of practitioners. And I can remember those days with workshops sponsored by US EPA and others, where Dave was out leading and educating a broad collection of engineers about this new area. Many of the things that he developed in the 1980s became standards in our industry as we moved forward and developed and matured as an industry. Methods that he developed for measurement, for example, have become essentially standards used worldwide. This one shown here is the ASTM D5084 flexible wall permeability test. Dave developed that standard with others collectively and is now perhaps the most widely used standard in the geoenvironmental area worldwide. So Dave certainly has had many contributions over the years. I think Dave is really, one of his attributes though is his leadership. He's been a leader in many different ways. He's led essentially the birth of and development of this profession in geoenvironmental engineering, gone on to lead a Department of Civil Engineering, taking a higher leadership role in a College of Engineering, and now at the highest levels of really maintaining and promoting the higher education for our young people in the United States. So I'd like to welcome our 2012 Terzaghi Lecturer, David Daniel.
Thank you so much, audience, for being here. Craig, for that wonderful introduction. It's especially a pleasure for me to be back here because when I got out of school with my master's degree, I went to work for Woodward Clyde in Emeryville, which is just a couple miles away from here. And I actually had baptism by fire in terms of construction inspection for the Clorox building. If you walked around, you see the Clorox building. I inspected the first pile that went in there. And in fact, I was down in the 12th Street BART station before there were any BART trains measuring the vibrations on the BART station. So on just a personal level, it's so nice to be back here. In fact, when I came out of school and went to Woodward Clyde, I showed up the first day and they said, "Oh yeah, Dave Daniels coming here. Where do they put him? Where will we put him?" And someone said, "Hey, there's an empty desk in Frank Fong's office." So off I went to Frank Fong's office, and Frank was here. Frank, I haven't seen you in 30 years. It's just wonderful to be back here in Oakland, and I'm so honored to be a Terzaghi lecturer, especially with so many previous Terzaghi lecturers in the audience. Well, I am going to talk about the geoenvironment. I think the literature is rich and speaks for itself, so I thought what I would try to do is talk a bit about the history of some of the key developments and key decisions, maybe a little bit about some of the people behind those decisions. I want to talk about the practice of engineering because there was a lot of resistance to change, especially when some of the research findings were not in sync with what practicing engineers were doing at the time. I'd like to tie that together at the end with some discussion about the New Orleans levees, which also had some safety issues. I had the pleasure of serving on the National Academy panel reviewing the causes of the Deepwater Horizon catastrophe in the Gulf of Mexico. And there are some common elements in these lessons learned that I'd like to speak about. As way of background, we'll be talking about waste materials, either in landfills or sites requiring remediation, that often have a cap above them and some sort of liner perhaps below them. I use the word system for liner because it often contains many layers and many components. I'm going to principally focus on the earthen liner or compacted clay liner. By regulation in the U.S., at least environmental regulation, that hydraulic conductivity or permeability, and I don't care which you call it, pick your favorite term, K, has to be less than 1 times 10 to the minus 7 centimeters per second. Where did that number come from? It came out of absolutely thin air with no basis to it whatsoever. And in fact, 1 times 10 to the minus 7 centimeters per second is about equal to 1 inch per year. And I always thought some engineer decided to confuse some lawyer by using 1 times 10 to the minus 7 centimeters per second instead of 1 inch per year, simply in an attempt to raise our hourly compensation up to that comparable to the legal profession. But worldwide, that is essentially the standard except for one country, Germany. Their standard is 0.5 centimeters per second as the maximum allowable permeability. And as best I can tell, that's simply a matter of German engineering principle. Whatever the Americans do, the Germans are going to be twice as good as that. The only technical basis for 5 times 10 to the minus 8 centimeters per second is at that level of hydraulic conductivity, chemical transport tends to be mostly by diffusion rather than actual physical movement of the water. And the liner thicknesses vary from less than a foot to more than 5 feet, but typically are on the order of 2 to 3 feet. There's a lot of work that was done by some people who are here in the audience that sort of laid the technical foundation for what I would call geoenvironmental engineering. Some of the great work on clay mineralogy, the early work was really pivotal. Roy Olson's work, which I'll tell you about a little bit later, Jim Mitchell's work, very important. Work on earth dams, compaction of soil to achieve low permeability. At Berkeley, the Army Corps of Engineers, USBR, Jim Mitchell with pioneering work. And of course, those of you from Georgia Tech will remember that George Sowers was the foundation expert for landfills and settlement and gas control. So as I was preparing this lecture, I thought, well, who was the first geoenvironmental engineer? Drum roll, that's your quiz. I don't know, but maybe it was Don Gray at the University of Michigan, and Don's here tonight. Don, it's great to have you here. Don was actually working on using trees to stabilize slope and really looking at the interaction of the environment and the soil, perhaps as soon as anyone else. Well, the transformative event in at least the regulatory environment is something called Love Canal from Niagara Falls, New York. And if you're too young to know what that is, it's probably some website we shouldn't go to. But if you're too young to know what that is, go Google it, find the real Love Canal environmental disaster, and read about it. So this was a canal that was dug in the early 1900s and abandoned after only 1 mile of it was dug. During World War II and after World War II, Hooker Chemical Company disposed of liquid chemical waste and drums of waste in the pits. In the early 1950s, the pits were covered with grass, and sure enough, people built homes around that. You can see actually the canal is this area that had been covered over. All these people built homes right next to what was in fact a ticking time bomb of disposed chemicals. In 1978, there was heavy rainfall and snowfall in the Niagara Falls area. The liquids leaked into people's basement. They spilled onto the surface of playgrounds. The Washington Post called it poisoned earth. The nightly news, night after night, the lead story was Love Canal. Anybody and everybody who had a health problem blamed it on Love Canal, and in fact, the nation was shocked at this problem. And indeed, it got people to pay attention. As importantly, it led to the creation of the Superfund law. The Superfund law, this is really interesting. The nation passed a tax on products to pay for cleanup of unregulated hazardous waste disposal sites for the public good. Imagine passing a tax with both parties supporting it. At any rate, it empowered the EPA to go after the polluters. And if they couldn't find the polluters to pay for it, for example, if they'd gone bankrupt, the taxes provided the money in the public good to clean up and remediate the sites. It also led to the Resource Conservation and Recovery Act, or RCRA as it's shown here, which was really the set of regulations that dictated requirements for treatment and disposal of waste. So for people interested in landfill design, it was the RCRA laws. And very important for me as a brand new assistant professor, they actually put some research money behind all of this. Well, one of the most significant set of research done in the geoenvironment was actually done by a soil scientist from Texas A&M University, Professor Kirk Brown. Under EPA sponsorship, he compacted soils in a compaction mold permeameter, we would call it. You can see a diagram on the right side. He put liquids, concentrated organic solvents, on top of the clay, and under very high pressures forced the liquids through, at least theoretically, through the clay. So he did control tests with water, first of all, to make sure that the clay soils were reasonably impermeable. You see permeability plotted versus pore volumes of flow. 1 pore volume of flow means an amount of flow through the test specimen equal to the volume of the void space in the test specimen. So with at least 1 pore volume of flow, one should have displaced all the liquid that was in the soil originally and replaced it with the invading permeant liquid. And as you can see with these 4, as it turned out, naturally occurring soils, all of the hydraulic conductivities were less than 10 to the minus 7 centimeters per second. So they were perfectly suitable soils in terms of getting low hydraulic conductivity. But when Brown and his co-workers replaced the water as the incoming liquid, and off to the left actually these data here are the water permeations, then they switched to, in this case, xylene, a non-water soluble, non-polar reagent-grade organic liquid, the hydraulic conductivity skyrocketed. They went way above 1 times 10 to the minus 7 centimeters per second. And what's going on essentially is that the organic chemicals cause a shrinkage, a sort of chemical desiccation. Now, perhaps some of you have experienced this yourself. If you've ever had, and I'm just told this is the case, so I'm not sure this is true, but I'm told that if you've had way too much alcohol to drink, you may wake up in the middle of the night very thirsty with dry throat. And the reason is that the ethyl alcohol tends to desiccate the cells, just as xylene will tend to desiccate clay. I'm just told that's the case. I can't confirm it. But Brown and his co-workers wrote, these observations suggest that soil liners cannot be relied on to retain organic liquids in landfills or surface impoundments. Wow, everybody was putting organic liquids in small or high concentrations in landfills. Everybody was using clay, basically Brown was telling the world that what we were doing was all wrong, and it was not well received. At any rate, the main criticism of Brown's research, aside from using very high hydraulic gradients, is that the shrinkage of the test specimens should cause the specimens to pull away from the rigid walls of the permeameter. And the argument went that, in fact, Brown wasn't measuring the hydraulic conductivity of the clay. Brown was measuring sidewall leakage around the clay, and therefore the test results were invalid. And I remember at the time thinking, well, the test results may be invalid, but what's absolutely clear is that these organic chemicals are very damaging to clay. And if you've never seen this yourself, just take some bentonite or other clay, mix it with water, and of course it'll make a nice moldable pottery grade type of clay. Take that same clay, don't do this in your home, mix it with turpentine or gasoline or something like that, and it will have no plasticity whatsoever. It will feel like sand, not like clay. Well, in fact, Messry and Olson had published data from a decade earlier. In the lower right-hand corner, you see the data for carbon tetrachloride and benzene, also non-water soluble chemicals, and you can see the hydraulic conductivities were way above 1 × 10⁻⁷. So as Professor Olson used to famously say, it should have been intuitively obvious to the casual observer that these chemicals were really bad for clay, and yet for some reason people seem surprised. At any rate, Brown got more money from EPA, got a lot of people coming in to visit him, got severely criticized for flawed tests, so they built some large-scale field tests, 2-meter by 2-meter plots. They were criticized for using reagent-grade chemicals, so they used real spent solvents from the paint industry, and they found the same results. The impacts were very significant. It reinforced the EPA's decision to ban liquid organic waste from all land disposal units. And in fact, it made the EPA very skeptical of clay in general. And indeed, they immediately latched hold of geomembranes as the preferred method of waste containment. So if you're a geosynthetics person, you owe your career to Kirk Brown and EPA's reaction to these test results. But most importantly for me, it caused EPA to give me my first research grant, first of many for about 15 years, to start investigating some of these issues. So we, as you'll see in a moment, used different types of permeameters and tried to sort out some of the testing variables. This is the consolidation cell permeameter that Roy Olson designed and built. You actually, you don't compute hydraulic conductivity from consolidation, but you literally flow water upward through the consolidation cell. It's really a wonderful device for measuring hydraulic conductivity. You just need to be careful that the permeating liquid doesn't dissolve the cell itself, but if you do that, all works out well. For the most part, we use flexible wall permeameters. These are really just triaxial cells, and the modifications were really pretty simple. We had to have different size base pedestals to test different diameter samples. And so typically we tested 4-inch diameter samples, and we had to make some parts out of stainless steel and Teflon so things wouldn't be dissolved, and we had to have more drainage lines to the top and bottom so that we could replace water with an invading liquid, for example, but otherwise it's pretty much a triaxial cell. So I had the pleasure of designing and working with machinists and building about 25 of these cells in our laboratory, and it required inflow and outflow reservoirs and pressure systems, and we had tubing everywhere. It looked like one giant spaghetti factory. But one of the very humbling things for me is when I wrote my proposal to EPA, I figured out how many liquids I wanted to test, how many gradients I wanted to test, how many replications I wanted to have, made that matrix up, and discovered it couldn't possibly be done. I had to use fewer liquids, fewer reps, and so forth. But it did require quite a bit of equipment. And of course, today, this is all much simplified. The flexible wall cells perhaps haven't changed that much, but the panel boards are much, much better for controlling flow. And in fact, the whole measuring system, set of measuring systems is much more sophisticated, including flow pump methods. One of the challenges we had to overcome is the fact that the latex membrane that you put around a triaxial sample is essentially soluble in the organic liquids that we were permeating these samples with. And so we had to find some way to keep the liquid from dissolving the latex membrane. I'll confess this was purely by accident. I was thumbing through a chemistry catalog and I saw a 6-inch wide roll of Teflon tape that was adhesively backed, and it was meant just to spread down and sort of tack to the surface of a countertop. And so I thought, what the heck, I'll buy it. It was probably $300 for the one silly roll. And we tried wrapping the sample with just one layer of Teflon tape, and it worked beautifully. It absolutely was spectacularly effective in stopping the organic solvents from destroying the latex membrane. We also had to find a way to keep some of the really nasty liquids we were using from getting into our hydraulic system. So Steve Troutwine came up with this device that he calls the bladder accumulator, which separates water, that's on the top of this diaphragm, separates water that goes back to your control system so you can keep it clean and uncontaminated and out of trouble for you from the permeant liquid, which may be very nasty, going on to the test specimen. That worked really well, and you could pick a flexible diaphragm material that's compatible with virtually any liquid. So there we go, flexible wall permeameters, Teflon tape, then latex membrane covered with accumulators and all sorts of systems. So here's what we found. One of the questions was, well, it's one thing if concentrated organic liquids destroy clay, but a lot of times the organic liquids are present in small concentrations. Do small concentrations also adversely affect clay? So here's some data for kaolinite. You see fixed wall cell. That's actually a compaction mold permeameter with no vertical stress on it. And the data for the flexible wall cell showing a bit lower hydraulic conductivity. But over on the left side, this is for pure water. Over on the right side is for pure methanol. You can see that with concentrated liquids and at least some permeameters, there were deleterious effects. Well, a whole bunch of research later, here is basically the story. Water is a polar chemical. You may remember that the H bonds are at, 105 degrees from one another, and so it's a polar molecule. That's why your microwave oven works, because the oscillating magnetic field makes the water oscillate. But things like heptane and xylene and carbon tetrachloride and benzene and gasoline, for that matter, are nonpolar. So the dielectric constant is sort of a measure of this parameter. For water, it's 80. For heptane or gasoline, it's 2. And experience has shown that as long as the dielectric constant is up fairly close to water, greater than something like 55 to 60, the presence of the small amount of organic chemical has no deleterious effect. In other words, there's enough polarity to the mixture that it doesn't create a problem. So if you have 100 parts per million of benzene in water, could that harm the permeability of at least these types of compacted clay? Absolutely not. There's just not enough organic liquid present. So it's really the concentrated organic liquid that is of concern. Those are no longer in landfills, but they're certainly in pipelines and in storage tanks. Another really interesting observation was that the effective stress acting on the clay has a big impact on its vulnerability to attack from concentrated organic chemicals. So the open squares in the bottom are a plot of hydraulic conductivity for the soil permeated with water versus applied. I should have effective stress on there. Applied effective stress, and it's pretty constant. Anything below the green dashed line is good. That's less than 10 to the minus 7 centimeters per second. The solid squares turned sideways up above are for a sample permeated first with water, then with methanol, which is miscible with water, then with heptane, which is miscible with methanol. So we actually did that sequence because the water-saturated clay will exclude the non-water soluble clay in the same way a water-saturated clay will exclude air that tries to get into the sample. Anyway, that intermediate solvent was just a way to get the heptane in. And you can see for vertical effective stresses greater than about 10 psi or so, there's not a terribly significant effect. And the reason is, remember, the chemical tends to cause the clay to shrink. That's only a problem if the clay cracks. And in principle, as long as there's enough vertical effective stress, the clay may shrink. In fact, it may just shrink to a lower void ratio. but it may not necessarily crack. This question came up in Professor Benson's Peck lecture the other day about GCLs, and I guess my guess is the same phenomenon is true with GCLs, but I think it's a great area for further testing because it's just a hypothesis. This also says, for example, perhaps not to have so much concern about deeply buried liners with high vertical compressive stress on it, but you ought to be terribly concerned, let's say with a liner near the surface for a secondary containment structure around a big oil storage tank, because there's almost no vertical stress on that near surface liner, and that clay clearly is vulnerable to attack. Well, if all else fails, you can just mix the clay soil with some sort of a stabilizing agent. And we, in fact, mix clay with sodium silicate, shown here, with lime and with Portland cement. And our theory was, well, if it's the shrinkage that causes the cracking, we ought to be able to add a cementitious material to the clay that will stop it from cracking. And that's precisely what happened with lime, Portland cement, and sodium silicate. It just sort of made the material sufficiently rigid that there was no shrinkage cracking, and the hydraulic conductivities were not necessarily impacted. So even if you want to use clay at a low effective stress, there may be a solution, but it probably involves some significant engineering. Let me switch gears now and start talking about field permeability, totally different subject. So I was sitting in my office one day, maybe a year into my tenure as an assistant professor, trying to figure out what the heck I was going to do to get research money and so forth, when a call came from somebody in San Marcos, Texas, which was about 40 miles from Austin, and he said he had a pond near their manufacturing plant, and the pond was leaking so fast they couldn't keep it filled with water. Would I come out and take a look? And I said, sure, I'll be right out there. So here's a cross-sectional diagram of this freshwater pond. The geotechnical engineer who had been hired to do this excavated 5 feet of clay near the surface to make the pond. They took the excavated clay and put it back in 2 6-inch thick layers or lifts to build a low permeability liner. It was a fine clay, plasticity index of 19%. The geotechnical report indicated that the permeability would be about 1 times 10 to the minus 8 centimeters per second, and the leakage from this pond, a completely unremarkable 0.07 gallons per minute. Well, the actual leakage rate was at least 20 to 30 gallons per minute. They had a water well to pump water into the pond, and they turned the water well pump on maximum, and they never could fill up the pond, so that was the leakage rate. So I calculated the permeability from that known flow rate, and it was 2 to 5 times 10 to the minus 5 centimeters per second. The owner drained the pond. Actually, all the owner had to do was stop the pump, and it drained itself. Very simple drainage. And I went around and looked at the liner. In fact, what I was really looking for was penetrations. I figured from what little I knew about roofs, if there was a leak, it was probably a pipe or something going through it that was not properly sealed. And there were no penetrations. That was not it. So I took some samples. Actually, I took one of Professor Olson's consolidation rings, hand-trimmed some samples from the liner, ran permeability tests in the lab, and got about 9 times 10 to the minus 8 centimeters per second. Still a permeability far, far less than the known value from the known leakage rate. So I thought, well, what do I do now? And I thought, well, let me try a bigger test. And I had no idea what sort of test to run, so I decided I'd just do a single ring infiltration test. I'd build a ring, embed it into the liner, and measure the rate of flow into the ring or into the soil. This is not a very good device because you cannot measure low flow rates. 10 to the minus 7 centimeters per second is only 0.003 inches of water level change, which is far, far less than the evaporation in Texas on almost any day, and too small in any case to really measure. You also have issues of lateral flow near the edges, but you can just draw a flow net and make that correction. That's not a big deal. So I bought some sheet metal, went out. This was an 8-foot diameter ring, filled it with water, covered it with a tarp. I thought this thing in the lower right corner was brilliant. This is a tube to measure the water level, and I put it on a slope next to a meter stick so I could get better resolution on the water level. But it turned out I didn't really need it. It leaked quite a bit. Measured the hydraulic conductivity. It was 5 times 10 to the minus 5 centimeters per second, which was almost exactly equal to the known actual rate from the full-scale liner. My conclusion was that the liner had been built and maybe it had dried out. They hadn't taken care of it, but in any case, it was in fact not a very good liner as measured by that field test. So I went to the EPA and said to them, hey, there perhaps is something anomalous going on between lab and field tests. How about if we do some more experiments? And they had plenty of money. It was that era, and they said, okay. So we built, actually Steve Day, my student, built 2 prototype liners at a site near Austin, Texas. Now, for those of you from Georgia Tech, this handsome man right here in the jeans with the shirt off is a young Glenn Ricks out there helping Steve Day. And down in the lower slide, this is Bill Eisenhower, who's right up here in the front row. And he'll tell me who that is. I think that might be Clark Morrison. But at any rate, our students were always so great in helping one another out. So we built 2 prototype liners with an under drain beneath so we could flood them and know precisely what the permeability was based on the flow rate that came out the bottom. We flooded them for 2 months. We, meaning Steve Day, did, measured the flow rate out the base, and calculated the hydraulic conductivity. So here are the results. Steve built 2 liners with a lower PI and a higher PI clay. You can see the laboratory hydraulic conductivities. I'm missing a second there on centimeters per second. We're in the range of 10 to the minus 8 centimeters per second or lower. The actual field rate measured from flow out the base was in the range of 10 to the minus 6 centimeters per second. In other words, our undisturbed sample, 3-inch diameter, thin-walled Shelby tube samples, underpredicted the actual hydraulic conductivity by 1,000-fold. And we wrote, quote, these results, coupled with other published data, lead one to question the applicability of laboratory permeability tests for predicting field hydraulic conductivities of compacted clay liners. Then things got really interesting because the industry did not like this finding at all. Hundreds, probably, of geotechnical consultants had run laboratory permeability tests on 3-inch diameter, thin-walled Shelby tube samples, certified as impermeable, their liners, and they didn't like any suggestion that that might not be correct. So I had a lot of people visit. I intentionally picked Air Canada for this airplane because I particularly remember them coming to visit me. There were 10 discussions published to the paper, which is a fair amount, but suffice it to say the industry did not like the implications that laboratory hydraulic conductivity tests might not be correct. And in fact, one of the valid criticisms was that this was just a test on prototypes, and I was so careful to use the word prototype in the title of the paper. Everywhere I wrote, prototype this, prototype that. Well, at least according to the consultants, the regulators ignored the word prototype and just took it as full scale. So at any rate, this is from one of the discussions. The writers believe that it is important that this study not be interpreted as a condemnation of clay liners. The writers have found clay to be a reliable material that can be used to construct low permeability liners. That was in essence the criticism. I was really taken aback by this, and I turned around to these guys and said, what do you mean reliable? How do you know it's reliable? There were no measurements whatsoever on how the clay liner was actually performing, and I would just say that's purely speculation on their part that there's reliable because these are buried in the ground, and if they leak, as Love Canal even showed, it may be decades later before the failure of that system to function would really show up. But the good thing was that led to more research funding. And the next EPA-sponsored research, they decided, well, maybe we better send this to a consulting engineer. So Bill Ellsbury worked for McClellan Engineers in Houston, and we were sort of the sub to them, and they were charged with building a full-scale liner, not a prototype, a full-scale liner. So they built an underdrain as well. This is a picture of the gravel. The clay liner would be built above that. This little pipe actually collects the underflow or the flow out of the base of the liner. They used what was common in Houston at the time, a pad foot roller. They tried it with the vibratory compaction on and off. It was a very high plasticity clay, 41%. They wrote the spec as they were normally writing, 4% wet of modified Proctor Optimum for the moisture content, and the dry unit weighed at least 90% of modified Proctor. It was only a 1-foot thick clay liner built in 2 6-inch lifts, and in that sense it might have been a prototype as well. They built a little pond around it so they could flood it. The result was that the field permeability was just terrible. It was 1 times 10 to the minus 4 centimeters per second, an absolutely awful clay liner, at least in terms of the hydraulic conductivity. Well, when we sort of studied, and Craig Benson did some of these tests, studied the actual clay, I thought the pictures were really telling. The photograph on the left, these are 4-inch diameter samples, straight out of the Proctor mold, if you will. You can see that this high plasticity clay on the left just was there in big chunks and clods. And if you're a gardener and you don't know anything about clay liners, and if you've ever dug in this clay that's so hard you can hardly break the chunks up, that's the kind of material that we're talking about. When we wetted it up to 16% water content and use standard Proctor energy, you can still see large voids between the clods. But when you wetted this clay up to 20% water content, look how wonderfully homogeneous this is. And you don't have to know anything about permeability to know that this sample is a lot less permeable than the two samples I just showed you before. It's also very clear that the energy of compaction has a big effect as well. And you may, students, you'll remember modified Proctor is about 5 times more compactive energy than standard Proctor. So these two samples were at the same water content, and yet the clod structure or large remnant pores are much, much less with the higher compactive energy. So especially for these high plasticity clays, the key is the clods. Your goal as a geotechnical engineer is to wipe them from the face of the earth, destroy all history that they ever existed. And you can do that one of two ways. You can either add enough water to the clods of clay that they're soft and weak and ineffectual and easily remolded into a low permeability mass, or you can attack them with an overwhelming force, compactive energy, and just pound them into submission and squeeze the chunks of clay together so that the large remnant clods are gone. Another key we found out was actually the interfaces between lifts or layers of clay. So this is a photograph of a 5-inch diameter, thin-walled, undisturbed sample taken of this 1-foot thick liner. And you can clearly see the lift interface at the bottom of the upper lift and the top of the lower lift. And those lift interfaces have a big effect. So for example, if you trace the green arrow here, imagine that there's a defect somewhere in the upper lift. And it spreads laterally at the lift interface until it finds another defect, including my use of the cursor, and so forth. So in essence, highly permeable interlift zones provide hydraulic connection between imperfections in adjacent lifts. And you could say, well, they're not supposed to be imperfections in adjacent lifts, to which I would say, nonsense. Why do we build these things out of 5, 6, 7, 8 lifts unless we assume there's some imperfection? In fact, we intentionally build redundancy in. So how do you get rid of these permeable zones at the lift interfaces? You make sure you roughen or scarify the surface of a completed lift before you put the next one down. You use rollers that have long, fully penetrating feet, and you pay careful attention to the issue. So now that we had built these various prototypes, it was clear that we needed to go out to large, full-scale, 3-foot thick liners and somehow measure large-scale permeability. So we came upon the idea of sealing up an inner ring in an infiltrometer device, the so-called sealed double ring. And by sealing the inner ring, and really the inner ring is the only measurement component here, by sealing this up, you can measure very low flow rates and avoid the problem of evaporation. However, the difficulty is you can imagine a falling head or a rising head test in this standpipe. As soon as the pressure changes, if it stays the same in the outer ring, that inner ring will tend to change in volume. And so you've got a hopeless measurement situation unless you make the inner ring out of 4-inch thick stainless steel. So, Steve Trautwein, I see Steve in the audience, came up with an absolutely brilliant idea. And the idea was to hook the inner ring up to a small, flexible bag. In this case, it's a medical IV bag that's hooked up. And the beauty of this is the pressure on this flexible bag is always the same in the inner ring and the outer ring. Even if the water level changes in the outer ring, the pressure in the inner ring changes by precisely the same amount. And when you want to measure the flow rate, you just close a valve, take the bag off, and weigh it. And you can come back and weigh, to 1/10 of a milliliter and get very precise measurements. And so, Steve, thank you. We came up with this idea, I confess, sitting in Steve's living room. The IV bags, his wife Lynn, who was a medical student at the time, is right next to him. She happened to have IV bags sitting on the coffee table. We were drinking beer, of course. we were studying this ethyl alcohol shrinkage thing, seeing if it really worked. And Steve, if I remember it right, looked at it and said, what do you think about this? And Lynn, had you not had those IV bags, I don't know that we would have ever come up with the idea. We also needed to track the rate of invasion of the wetting front into the compacted clay, because to compute hydraulic conductivity, you have to know hydraulic gradient, and that means you need to know where the wetting front is, how far down it's penetrated. So tensiometers are just negative pore pressure measuring devices, and we put them in at several depths to measure the rate of penetration. So here's the typical setup. The inner ring is 5 feet square, shown here. This is the outer ring. They're sealed in bentonite trenches. These are tensiometers being put in place. And then this whole thing is flooded with water, the IV bag connected, and then we start measuring, which takes weeks or months sometimes if the liner is really good. Nobody liked this test. It was the hated test. I remember once doing a short course, and we were sitting with somebody in a bar. There's a trend here, I admit it, on 6th Street, and there was some guy walking by, and he was the most depressed-looking guy I'd ever seen, one of these bums, if you will. He was just depressed as hell, and we were with a consulting engineer, and he leans over and says he probably just found out he has to run an SDRI test. So, these were time-consuming, expensive. It takes months to find the results. Nobody liked them, so everybody started hunting for a quicker, faster, cheaper way. And one of those was just a 2-stage borehole test. You just seal a casing in the ground. In stage 1, the casing is flush with the bottom of the hole. You take the top off, extend the hole down below the casing, and run a second stage. You can actually calculate vertical and horizontal hydraulic conductivity. I call this Boutwell test because Gordon Boutwell championed the test. This is Gordon actually tamping bentonite pellets into the annular space between the casing and the borehole. Here I am with about as sophisticated task as I was charged with, which was pouring water into it. And here's Gordon. It's just a falling head test, which you could run pretty quickly and inexpensively. And pretty quickly, the industry started saying, well, couldn't we do like 5 of these 2-stage borehole tests instead of 1 SDRI test? And that was a really attractive alternative just from a practical standpoint. Well, Craig Benson, thought, well, all right, I'll just take really big samples. So Craig, the indomitable person, decides he'll hand-carve 18-inch diameter samples out of the completed compacted clay liner. There's his trimming tool. He developed a sharpened steel device, a knife, if you will, to slice off the bottom of the sample. Then he shipped it back to the laboratory for testing. So up in the upper right is a traditional, regular, flexible wall permeameter. Here's his Texas-sized permeameter that he took to Wisconsin. He needed his pickup. That gave him the excuse to buy a pickup. And just for scale, he put his son Austin there. Austin now is about to graduate from Cal Berkeley and go to Stanford. So maybe that's a good thing for you people with young kids. Put them on a permeameter, and that just goes to show. Where's Professor Stokey? Focusing on permeability instead of shear wave velocity leads to very good things. So here's what Craig found. What they did was they plotted the hydraulic conductivity versus the diameter of the specimen. And as you would expect, as the specimen got bigger, the hydraulic conductivity got bigger because your chances just became greater of getting some macro scale feature captured in the test specimen. But as you can see, once they got to the vertical green line, which is about a 12-inch diameter specimen, any larger than that really didn't tend to have much of an effect. You can see the graph is essentially horizontal after that. So that seems to be a big enough sample size, at least in typical compacted clays, to get good results. So, armed with these measuring devices, we and others went around the country. That's not the proper way to test a monitoring well for toxic organic vapors, by the way. And so many different kinds of compactors by different kinds of people, SDRI tests and other tests run at many sites. And the great thing was phone calls from virtually everybody doing this, and I was just really in a privileged position of essentially knowing what everybody was doing because I was everybody's connection to the US EPA, and it just provided a tremendous wealth of knowledge. And for young academicians, I cannot emphasize enough how useful it was for me, at least, to have deep connections to practice because it really helped to guide the research in useful ways. So what did all this show? This is from a paper with Craig and Gordon Boutwell, in which 85 full-scale liners were tested. These were all certified full-scale, all had the Good Housekeeping stamp of approval from a professional engineer. This was industry standard practice back in the 1990s, 85 tests. Well, the horizontal green line is the magic 10 to the minus 7 centimeters per second. So everything below that is great. That means pass. Everything above it is not good because that's a field permeability greater than 1 times 10 to the minus 7 centimeters per second. And one thing you'll notice is that there are a fair number of points above the line. As of that time, the industry still had not quite figured out how to do this right all the time. Perhaps even worse than that, double not good, is the areas shown in red here. And those are data points representing liners that had field hydraulic conductivities greater than 1 times 10 to the minus 7 centimeters per second, but laboratory measured hydraulic conductivities on Shelby tube samples less than 1 times 10 to the minus second. So in that red zone, it means the lab test indicates passing, whereas the presumably more representative field test indicates failing. And that's a very unconservative result for an engineer when an engineer says something's good and in fact it's not good. This parameter P sub 0, I believe Craig came up with that terminology, but that I'll define in just a minute. The most fundamental problem is that the way the usual compaction specification is written for clay liners is flawed. It's deeply flawed. And so often the specification is written this way. Imagine that the red curve is a compaction curve, say standard Proctor, for example. Typically, the design engineer will know that they should compact wet of optimum, so you have to be to the right of the curve in terms of the moisture content. And by tradition in fills, you specify a minimum dry unit weight. For example, 95% of the maximum dry unit weight, let's say from standard Proctor compaction. And that means that brown crosshatch zone is the passing zone. Those are moisture contents wet of optimum and above, say, 95% of standard Proctor compaction. Well, this number P sub 0 that I mentioned before is actually a measure of how many of the field measured moisture density points are on or above the line of optimums. And a line of optimums connects the peaks of compaction curves developed by different energies. So in this example, there are 10 dark circles there. 8 of them are on or above the line of optimums. And so the P sub 0 is 8 points on or above the line of optimums divided by a total of 10 points or 80%. And experience has shown that the higher that number, generally speaking, the better off you are. The more of your moisture density points on or above the line of optimums, the better off you are. The problem area is the lower left corner of the traditional compaction specification, the red crosshatch area and the red points here, because that's not on or above the line of optimums. But I might explain it this way. Imagine a point on the lower left corner of that zone. And imagine what the real compaction curve would look like for that point. The lower left corner may be wet of the optimum for the higher compaction energy, but when you go to a lower compaction energy that would pass through the lower left corner, it's actually dry of optimum for that particular compaction energy. And that's at the heart of the problem. The variable density may in fact lead one to be dry of optimum with the actual way that the soil is compacted. So what do we recommend? This is the procedure that I recommend to you. The way I would suggest is that you realize that you'll never know exactly what the field compaction energy is. So I try to bracket in the laboratory. So the blue curve, look at the lower diagram first. The blue curve is a compaction curve with modified Proctor. I doubt that you're going to exceed that in the field. The red curve is standard Proctor, and the green curve is reduced Proctor. For example, standard Proctor compaction techniques, but fewer drops of the hammer than you would normally use with compaction with standard Proctor. So my sense is somewhere between the green and the blue is reality, but we don't know where it is. And so what we do then is we start compacting soil samples. So I just had a white dot show up at the left side of the blue curve. So you compact up that sample at that moisture density level, and then you run a permeability test on that. So now a circle just popped up on the corresponding hydraulic conductivity plot at that same molding water content, and that's a really bad sample because the hydraulic conductivity is above the dotted line. It's greater than 1 times 10 to the minus 7 centimeters per second. That's a fail. That's not good. So we keep going. There's another circle that just popped up around optimum in modified Proctor. We run a permeability test at that molding water content on that sample, and the hydraulic conductivity is still unacceptable. So let's keep going, use a higher water content. You see a check mark just appeared. That's the moisture density point. When we run a permeability on that sample, you see the check mark on the hydraulic conductivity curve. That one's less than 10 to the minus 7. So the checks are good and the open circles are bad. So now let's go to standard Proctor. Same thing, we compact a sample, run a hydraulic conductivity test, and you see on the red curve up above, the circle showed up. Not good in terms of hydraulic conductivity. Let's keep going. There's one that happens to give a good hydraulic conductivity and so forth, and then let's do it for the reduced Proctor and so forth. So the checks on the lower diagram basically gave satisfactory hydraulic conductivities in the upper diagram. Then what you do is you draw a moisture content density specification that encompasses the good points and rejects the bad points. That then becomes a rationally based moisture density compaction specification based upon variable energy of compaction. And I would submit if the field values are in that green zone, that's about your best chance of getting acceptable hydraulic conductivity. Well, you can also use this method when there are other criteria because hydraulic conductivity isn't the only thing geotechnical engineers worry about. Shear strength, for example, is one of those. So you can do this series of tests for hydraulic conductivity and do the same thing with shear strength. It could be, for example, unconfined compression strength. It could be interface shear strength between the compacted clay and a geomembrane. And of course, when you do shear strength criteria, you're going to tend to exclude the low density, high water content points. So the brown zone, not surprisingly, is higher density, lower water contents. But with any luck, if the gods of permeability and shear strength are shining on you that day, there will be a zone that both provides acceptable hydraulic conductivity and acceptable shear strength. We've done this as well with desiccation potential, just measuring shrinkage cracking. You could put other parameters in as well. I wish the industry would do this more often, and I wish the industry would abandon the completely arbitrary way that moisture density curves are typically written. I'm not saying they aren't perfectly fine for structural fills, but honestly, the most dangerous person on a clay liner job site is somebody who's only done structural fills and they've never done a low permeability clay liner because the rules are different when you're dealing with these thin liners. Let's shift gears again. So there's another miracle, a new kid on the block. Somebody develops a commercial product, a thin, prefabricated layer of clay to replace a thicker clay liner. The SDRI tests are done, all this compaction stuff is done, bonding of lifts, all that's out the door. You just unroll these blankets, declare victory, and move on. You know, the perfect answer for all the troubles that building good quality clay liners give you. There are several kinds of geosynthetic clay liners, those that are encased between geotextiles, bentonite in the middle diagram, mixed with glue and attached to a geomembrane, or some combination below that. Well, how did GCLs get into this business? Actually, the first guy to use GCLs was a guy named Bill Schubert, working for Chemical Waste Management on the CID landfill in Calumet City, Illinois. And this is a typical diagram of a hazardous waste double liner system in use at that time. And the problem was they built these liners, went to all this trouble in public hearings to convince everybody that these things were safe. But the reality is that geomembranes sometimes contain small imperfections, pinholes, if you will. And that can lead to leakage to the primary geomembrane liner and did lead to leakage in waste management's facilities. So they just built these sets of facilities, and suddenly, almost instantaneously, moderate amounts of flow are showing up in the leak detection layer. And of course, we didn't call it leak detection layer, we call it secondary flow collection system, but still everybody thought of it as leak detection layer. So you've got this brand new Cadillac hazardous waste site, and at least in some people's eyes, it's leaking right away. And Bill said, what can I do to stop that? So his idea was to put a GCL under the primary geomembrane liner so that through those pinholes, of course, the liquid would tend to pass, but it would hit the GCL, which would essentially stop the flow and make the flow in the leak detection layer go away. And so that was, in fact, the first application. And as you might imagine, it worked great. I mean, it did exactly what Bill wanted it to do, and Waste Management continued to use it. Well, if a composite liner with a thick compacted clay liner is good, might a composite liner with a geomembrane and a thin GCL be just as good? And of course, the industry would love the answer to be yes, because the thinner liner saves a lot of landfill volume, and actually when you do the math, there's a lot of value there. If you add 3 more feet to the volume of a landfill and multiply that by the price of the material, it's almost like free money at the bottom line for the facility owner. It's much faster and infinitely easier than compacted clay liners, typically much less expensive than compacted clays, and maybe as importantly, there's just a lot less uncertainty, especially about schedule. You don't have to build test pads and wait months. You're talking about days with certainty, not months with uncertainty. So the GCL salespeople came to us. Of course, I asked EPA for money, and they said yes. Those were the good old days. And I'll confess, I was very skeptical. The salespeople came up to me and said, you just overlap these panels and they seal themselves up. And I said, I'll believe it when I see it. And so by then, I was pretty skeptical of small-scale tests. So we built some large tanks and decided to test the overlaps to see if they really worked as they were supposed to. Here's one of the GCLs. This has thin geotextiles on both sides, so there's no bentonite that goes in between it. The manufacturer claimed that the bentonite, when hydrated, oozed through the openings in the geotextiles and magically sealed up the overlaps. Here's polyester now. Some of the GCLs require extra bentonite along the overlap. And, I must say, I have been rather appalled to hear that sometimes owners and their consultants recommend leaving the bentonite out on these materials with thicker geotextiles. That may be valid in some cases, but clearly the bentonite is needed in a lot of cases. Here's the geomembrane-backed GCL. This has the geomembrane side facing up, the black surface being overlapped. We filled the tanks with gravel. That was a tough one for Paula to shovel all that gravel out. She graduated with significantly enhanced upper body strength and an education. What more could you ask for? And filled the tanks with water, measured the outflow rates. And here's what we found. The middle column are the control tests with no overlap. The far right column are the tests with the overlap. And indeed, the overlaps worked great. There was virtually no difference in the average hydraulic conductivity with and without overlaps. And notice for C, that was the geomembrane-backed GCL when they overlapped it. We had absolutely no flow in 5 months. And when I peeled back the overlap, the water had only migrated about 2 or 3 inches into the overlapped area. It didn't even get beyond that. Well, that led me to wonder, well, what about bentonite sort of sandwiched between 2 geomembranes? And so we decided to just put a GCL, geomembrane-backed GCL with the geomembrane side down and the bentonite up, put defective geomembranes, this one had slits and holes in it, cover it with gravel, flood it with water, and see what happens. Well, 5 months later, Paula excavated the gravel. I love Paula Esternell. And we looked at what the bentonite was like, and you can see the wetting patterns here. Actually, the water penetrated minimally into the bentonite because such a great seal was formed between the geomembrane and the bentonite. So my favorite lining system is actually, in some ways, a geomembrane with bentonite sandwiched between 2 geomembranes. And the reason why I like this system so much is you can imagine an occasional imperfection in the overlying geomembrane. Well, for water to get out, it's got to get into the bentonite, hydrate it, and the calculations show years for it to get, a meter or 2, hundreds of years actually, to get many meters, to find another outlet at the bottom and somehow get out. And you can imagine how incredibly impermeable this system would be. In fact, it has only 2 drawbacks. One is bentonite, when it does get wet, is very slippery and low shear strength, so you use this with caution on slopes. And the other concern is sometimes crazed construction workers puncture holes in things. And so this, because it is thin, is vulnerable to puncture. To that, I would say put maybe 12 inches of a clay liner below this, so you've got this system sitting on top of something that's completely puncture resistant, and to me, you have a phenomenally impermeable liner system. So we have learned that the bentonites are vulnerable to large changes in hydraulic conductivity from chemicals. Back to the slide from Messry and Olson, and Professor Benson covered this beautifully in his lecture. Thin liners are vulnerable to damage, and I think that does bring into question redundancies, and good engineering requires that one think about redundancy. Diffusion becomes an issue with thin liners of any type. And I guess the biggest problem I've seen with GCLs is overzealous salespeople convincing people to buy GCLs and use them in applications for which they shouldn't be used. I remember talking to one of the GCL manufacturer's engineers early on in this, and I said to him, "What's your job?" And he said, "My job is to keep the salespeople in check and keep them from doing something really dumb." So do be careful about the applications. And of course, slope stability is a critical factor. I'm not going to describe in detail these full-scale tests that were done with Rudy Bonaparte and Bob Kerner, but slippage did occur on 2-to-1 slopes. I guess what really struck me about this is if any one of the consultants had run interface shear tests on these materials, they would have concluded that this slope would fail. It's amazing, though, when you do something in the field and you actually see it happen at full scale. It's just phenomenal how human nature plays into this. And, Rudy Bonaparte can show as many interface shear tests as he wants, but when you do this and you build it and you actually see it in the field, it does have an effect. I think we have a pretty good grip on interface shear factors, and I think it's just a matter of following best practices. Well, I mentioned that I had the privilege of working on the New Orleans levees and Deepwater Horizon, and I'd like to close this conversation out really with some reflections upon safety and the extent to which engineers do or do not let safety drive their engineering. And for the New Orleans levees, I want to focus on the 17th Street canal failure. It was a very intensively studied canal failure. Here's a cross-section of the site where the failure took place. The levee in the gray is on marsh, which is on very soft clay, and the brown underlain by sand. The design offices of the Corps over decades, and so one thing I want to make clear, I'm not blaming any person here. This is actually processes that took place over many decades, many consultants, many leaders. But at any rate, the decision was made to use a factor of safety of 1.3 for global stability of this wall. Now, I remember when I worked here in Oakland, I would never use a factor of safety of 1.3 except a temporary slope where nothing bad would happen if it failed. Now, if those of you who are geotechnical consultants routinely use factors of safety of 1.3 or less, I stand corrected. Practice has evolved. But to me, at least, I would say that is a very strange factor of safety for a safety-critical design. Now, granted, the hurricane's only going to load this up once every 50 years, and it's only going to load it up for about 12 hours, and then the water will recede. And in that sense, it's very tempting to use a low factor of safety. But we all know when you think about factor of safety, number one question probably should be, what's the consequence of failure? And as it turned out, it was discovered that, among other causes, there was a water-filled gap that developed behind the wall. In the lower diagram, you can imagine the factor of safety is lower for that failure mode, but that wasn't recognized at the time of design. So the graph on the left is a plot of shear strength versus depth. So going down is increasing depth. Going from left to right is increasing shear strength. And when I was in practice here, we'd do this all the time. We'd run our tests, plot shear strength versus depth or elevation, and then came the real art of engineering. I had to draw a curve through that became the design curve. And that is an art because you need to take into account lots of different things when you're thinking about shear strength and what design profile that you will use. Well, the design profile actually used, this dates back about 4 decades, is the yellow line shown on the curve. So all the points to the left are shear strength measurements lower than the design curve, and all the points to the right are shear strength measurements that are higher than the design curve. I, to this day, have no idea why the designer didn't draw this at the left end of those circles. I would have drawn it in a way that was more conservative than is drawn here, unless they knew something that they didn't write down that I don't know. It was not a conservative interpretation of the data. Furthermore, you can think about averaging sometimes for vertical piles where you integrate vertically and you'll be a little higher and a little lower. But a long wall, in many respects, is like a chain where the weakest link will fail. Well, along a long wall, the weakest 50 meters of wall or soil along the wall is, in fact, the most critical one. So averaging would be no more appropriate in that circumstance than I would say averaging the strengths of a bunch of chain links would be in figuring out what the strength of the chain is. And remember, the factor of safety was only 1.3. So in obtaining soil samples for shear strength measurements, the engineers drilled exactly where I would have drilled, at the crest of the levee, because that's the easiest place to drive a drill rig. But the failure surface didn't limit itself to underneath the crest of the levee. The levees had been in place for decades, so the soil was fully consolidated. And in fact, the strength at point B was considerably higher than the strength at point A. Soil mechanics 101, I would say, and yet that was not taken into account. They used the strengths at B rather than A. So the research branch of the Army Corps of Engineers ran a fascinating test called the E99 test on the Atchafalaya flood basin. This was not in New Orleans itself, but very similar soils. And they loaded this test wall up with a design water level of 8 feet and a factor of safety calculated of 1.47. And as you can see, at 8 feet water level, the curve is turning horizontal, right? You're approaching infinite deflections with very little change in water level. Now, we boring engineers don't want to be on that part of the curve, right? We want to be on the lower left part, where even if we're wrong a little bit, nobody pays any attention and life goes on. Well, the research report said, although the test wall was not loaded to failure, failure may have been imminent. And the remarkable thing to me is that failure was imminent, but nobody said, but the factor of safety was 1.47. What are we missing here? Maybe we ought to go back and look at the designs and figure out what was missing. But you know, that happens in so many organizations. You know, one group finds one thing and somehow it doesn't make its way to the other. The Deepwater Horizon disaster, which caused the loss of more than 10 lives, truly was a disaster, and I'm not going to spend much time on it, but I do want to point out two findings. First of all, just before the explosion, the crew did what was called a negative pressure test. With the drill pipe in this 18,000-foot deep well, they put a packer around the drill pipe and essentially lowered the water level inside the drill pipe. So if the cement seal down at the base of the well was tight, the water level would not rise. And that's why they call it negative pressure, because you lower, in essence, the fluid pressure inside the pipe. They did the test 3 times. At best, one would say the results were ambiguous. At worst, you would say it did not confirm at all that the seal was right. And I won't even go into the questions about the cement and the lack of testing and so forth. Suffice it to say, they did not have a clearly passing test that was the critical test. They also had a blowout preventer, which actually didn't prevent the blowout. It did actually actuate. And they have 2 shear rams that are designed to shear off the drill pipe under extreme circumstances, and it did actuate. But the blowout preventer is designed to work only when the drill pipe is in tension and the drill pipe is centered in the well. And there's no joint between drill pipes at the intersection where the blades go, which means it was meant to be a carefully controlled shearing. And imagine this, it's your last desperate act. You're going to shear off the pipe. It's going to cost millions of dollars to go open that well back up. And yet it was designed for controlled conditions. In fact, there was an explosion. The pipe was not in tension. It was in compression because the rig at the top was gone. The pipe was not centered because with thousands of feet of pipe, it tended to buckle, so it buckled up against the inside wall of the pipe. And because it was in compression, imagine trying to cut a string. It's easy to cut a string when it's in tension. If it's in compression, it's not so easy. So the compression actually jammed the pipe into the jaws of the device, and it never closed all the way, and the liquid went right around it. Our report from the National Academy said the lack of a strong safety culture is evident in the multiple flawed decisions that led to the blowout. So I thought about sort of these 3 different things, the work in the geo-environment, especially in the early days. And item number 1, I would say in all 3 cases, safety was not the top priority. I think of the consultants who were in denial about organic chemicals, the consultants who didn't want to challenge whether the small-scale lab tests were valid. New Orleans, I'd blame Congress as much as anyone for putting so much financial pressure on the Corps. And clearly with Deepwater Horizon, as they made decisions about what to do with the negative pressure test, for example, safety was not the top priority. It's so interesting in item number 2 that people ignored or chose to ignore some really vital test results, the permeability results, the field results, the E99 test results. I'm not sure ignored is the right word so much as didn't get incorporated into the culture of a complex organization. Item 3, a common element is that these techniques suggest a disruption to standard engineering practice. Moisture content density test, that acceptable zone, different from standard practice. Field testing on test pads instead of laboratory tests. In the case of New Orleans, the higher design hurricanes, the information from the E99 test would have all disrupted standard practice, and certainly the oil industry was very confident in its procedures and is not desirous of any disruption. And finally, in the early days of the GEOenvironment, there was no environmental regulation. And in fact, it was only, as much as you like or dislike the federal government, without the EPA coming in with the heavy hammer of enforcement as codified in law, I don't think nearly as many changes would have occurred. And in fact, in Katrina, I wish there had been more peer review, Bill. I wish the Corps had been given more money to do it right. I think they would have done it right. And certainly in the case of Deepwater Horizon, there was almost no technical oversight and regulation of things like the negative pressure test and so forth. So those are some of the common elements. The first canon of the ASCE Code of Ethics says engineers shall hold paramount the safety, health, and welfare of the public. And if there's one integrating message from these cases, I think that's even more true than ever. So when you go home proud that you're an engineer, I hope you go home proud that you're upholding this ethical standard. It's a very important one. And from my experience, the main two issues are when something comes along that is disruptive to the status quo, everybody's natural tendency is to stick with the status quo. Whether you're a hard disk drive manufacturer in the computer industry and somebody comes up with a better way of doing it, or you're a consulting engineer with a perfectly fine and healthy practice, your natural tendency is to, let's say, dismiss, if you will, things that are disruptive. I would just suggest that you pause a little bit more, put your engineering hat on, and think through whether perhaps it requires some more thought. And I do think cost pressures from the owners or clients clearly in all of these cases were a huge factor. Congress in the case of New Orleans levees, and I think ultimately the owners in the case of some of these waste disposal facilities. So where do we go from here with the GEOenvironment? Well, if I were a young professor, I'd be all over new materials, geosynthetic materials, trying to find better ways to make bentonite, adding materials that will attenuate chemicals. Sustainable environmental controls, I think, are a really interesting topic, especially for landfills, so that you don't just throw it away and walk away from it, but you make them digesters or processing units. I think the interactions with the components or systems engineering is a really interesting question. I was talking with a student yesterday concerned about temperature effects in landfills and how that might influence the behavior of the whole system. And if we've learned anything from these complex components, it's the way those components interact that perhaps is more significant than the individual components. And I think that's where the real art and expertise lies. As the world changes towards megacities, I think there are enormous opportunities for geoenvironmental engineers to figure out how we're going to cope with all of that. My favorite topic is carbon sequestration. You know, there's just too much carbon up in the atmosphere. Let's just get it down into the oceans or back into the earth. Let's isolate it in the earth. So I'd love if I were, straight out of school with my PhD to spend my career on trying to figure out how to isolate carbon in the subsurface. And of course, clean water is a huge factor for our planet. I think these designs ought to be better informed by risk. So if you're interested in risk assessment, I'd say this is a wide open area. And for any of you who are a little bit in touch with the softer side of the sciences, I would say trying to marry organizational behavior trends and human psychology with how organizations actually work to implement a safety culture, and a lot's been done in the chemical industry with safety culture. I think this is a great area for further research and development. Well, let me close by saying thanks. No professor would have ever done anything worth anything at all without wonderful, wonderful students. I am just deeply and profoundly grateful for the intelligence and the drive of these great students. None of this would have happened without them. And my faculty colleagues were so instrumental. My mentor in life, Roy Olson, is here in the front row. So my biggest question is whether he approves or disapproves of the lecture. I can guess, tolerably adequate is my goal. That's actually pretty good. Steve Wright is not here, but I benefited so greatly from conversations with Steve Wright about compaction. He's one of the smartest people I've ever met and was just deeply helpful. Bob Gilbert's been a great colleague. Ken Stokey always set a high bar for everyone. I was just so lucky to have these colleagues. Professional colleagues in the upper right, Bob Kerner, Rudy Bonaparte is here. It's been great to work with him, Steve Troutwine, and the many, many people I worked with on short courses. And of course, my family is very important to me, Alex, Catherine, and Alex, and Susan keeps me humble, that's for sure. And finally, to the 3 universities where my work was done, students and colleagues there, and especially ASCE and everyone in the audience. Thank you so much for the honor of addressing you today. Thank you.